So a couple of quick notes before we go any further. Take a look at your assignment this week in week 14 folder. Notice it is for bonus points only. And I have taken out the discussion board this week. So the only thing you actually have to do is the test. The test, however, has some questions about things like subnetting that are in some of the material we want to talk about today. So make sure you pay attention to some of these pieces on subnetting. When we made you guys learn binary, this is one of the reasons why your computer works in binary, and we have to figure out some tools to use. And you've seen these things. You just didn't know what they look like. So I'm going to jump ahead a couple. So we want to look at how do I break my network up. So we either want to break it into smaller pieces or we want to add it to a bigger network. So before we've looked at how do I add my network into the big World Wide Web. What we also need to think about is how do I break my network up for things like security. So if I have wireless access points on my network at home or at a company, maybe I want to allow guests on there, but I don't want to allow them access to all the important files on my network. How do I break up those networks? So sometimes it's a matter of performance. It can be a matter of troubleshooting. So one of the tools and a term you have seen is this thing called a subnet mask. And so a subnet mask really just takes that IP address that we know your computer gets, and in most cases gets given, and it says, okay, this is what we're going to do to divide it between the network portion and the host portion. In other words, the portion we don't control and the portion we do control. So if you remember back when we set up your router, we had an assignment where you had to look at a router, and you had to set up, I'm going to have an IP address here, and I'm going to give it a certain range. And we know that we have some numbers that are unique, like 192s. Anything with a 192 we know is an internal address for our network. There's also 172s and 10 ranges. So for the class A, B, and C networks. So that subnet mask comes into play and says, here's a second piece of that. So here's our IP address you're given. This says, here's that mask, and it's usually written, the one you'll see most often in a Class C network on your home router is UC 255.255.255.0. And what that looks like when I write it out in binary then is it's all ones until we hit that last octet. And if I look at those two, we can see that it makes a sliding pointer. You can almost think of it that way. So which portion is the network? Which portion is the host? So it allows us to divide up our networks a little easier. So these are the most common ones, Class A, B, and C. And so in this, so a Class C says there's 24 bits. 24 bits here are used for network, and that leaves only 8 bits then for us internally. And 8 bits, we know 2 to the 8th power, or 8 bits, is 256. So a Class C network, we know, can have up to 256 addresses in it. Well, not quite, because 2 of those are reserved, the top and the bottom. So we have 254 addresses a company could use. And you think, well, that's a lot of addresses. But is it really that many? Is it enough for Peru to work inside of a Class C? Is it enough for your house in some cases? Start thinking about all the devices we're starting to connect. You have thermostats. You have your lights are being controlled by those. So even a lot of large houses, it's not big enough to control that. But I don't need to go to a Class B address in some cases. And so we can actually do this technique called subnetting, where instead of just these 3 defaults, we can maneuver this sliding pointer one way or the other so we can have networks of whatever size we need. So that happens in something we call CIDR. And CIDR you're going to see more often, and you've probably seen it, you just don't realize what it is. So CIDR, classless interdomain routing. So instead of just those preset class 1, 2, and 3 addresses, or class A, B, and C, so you don't have a company like IBM getting 16 million IP addresses. We can put that pointer, that sliding pointer, anywhere. Anywhere. And so the way we do that is we say we have an address and we have a /24. And the 24 says how many of those ones are in there. So a class 24 /24 really is that class C network. But if I said it was a /25, then it'd move over one to the right. A class 23 would move over one to the left, as I throw things at you there. So this is a way we can start to break up our network. So think if I'm an internet service provider, I need to be able to do this, and even in my company I start doing it. So why do we want to do that? Maybe we want to break our networks up, maybe for security, maybe we need better performance. We can start breaking our networks up into smaller pieces. And so one way might be we break up every floor in a building into a separate network. To do that, we're going to need to break them into smaller pieces. And we can do that through using that idea of subnetting or CIDR. So an example like this. Here we have different floors, and we put them on different switches. Then each one of them then has a router. And so we break them into smaller chunks. The biggest reason we do that anymore is that idea of security, so that we can have a subnet for each floor. Maybe we're renting out our business for different businesses. We rent out our building, but we're going to provide internet connection for them. We could break them into subnets that way. Maybe, again, it's a company where we have a lot of information that's very proprietary. Think about here at the college. We have information at the financial aid office that we can't disseminate to anybody else. We need to protect that, and so one way to do that would be putting them in their own subnet. Because by default, I can't get from this subnet to this subnet unless there's a router rule that allows me to send that packet. So I actually have to have a router in place to do that. Now, if you look at the difference between this and that other picture, we substituted switches for routers. So one of the things that you're going to find, now that our switches have gotten more and more powerful, so we no longer have just layer 2 switches, we have layer 3 and layer 4. We really are combining a switch and a router in a lot of cases. And so when we do a layer 3 switch, in most cases it can actually handle this idea of being able to route some of that traffic. So just something to keep in mind. So class A, B, and C we already looked at. We know that those have limits of how they work. But if I go look at this table for subnet masks, now we have a group of masks for a lot of different numbers. So here's our class C right here at /24, and it says we can have 256 subnets, and each one can have 256 or 254 clients. And so these are sliding scales of how many we want. So if I go all the way to that subnet mask on the top, so a /17 designation, I get 2 subnetworks, but each network can have 32,000 devices on it. So we can pick in here how many networks we need and how many devices we need inside of each network. And so for a lot of companies, like I said, here's our /24, our class C. We could have, in theory, 256 networks, but each network can only have 254 devices. And for a lot of companies, this is something we've done, is we've said, okay, we now have too many devices, and we've moved that up, and so now we have fewer total networks, but more computers in each network because of the sheer number of devices. Especially now that we've got the Internet of Things and all these sensors and devices, that's one we've done really, really commonly. So this chart is a handy shortcut way, instead of doing all the math, of showing you what some of those are. So this is what internet service providers do. In a lot of cases, they go this direction because they have a lot of clients. So from a single IP address, they can get 16,000 different networks and assign each customer a network with up to 2 IP addresses. So for your house, that works really, really well. They give you an address, and so now that phone company has leveraged, or internet service provider has leveraged their side to get that. So if I look at those WAN numbers that we get, and you can find some of these in a lot of different places. So if I do right now, you're going to see them again. So we do a CMD, and I do an IP config /all, so we get all of the information. These numbers show back up. It's a little harder for me to see in here. Ethernet adapter 2. So in this particular case, when I look at this one, my VirtualBox one says I have a IP address of 192.168.56.1 with a subnet mask, a class C of 255.255.255.0. But when I look at what the actual physical connection is, so here in my lab, here's the address that my router provides. So it says our address is 192.168.180, and it provides that 101 from DHCP, and it says, all right, here's a Class C address. And in this lab, that works really, really well. We don't have more than 255 computers in here. It works well for all of the pieces we do. But the address I actually get that goes to my router, so the device that comes in here, so if I look at our routing device, log in. Do it in a different browser because it's not going to like that. All right, so if I look at details about this particular one, so my incoming router address, that's how it actually addresses it. It says, I'm going to call it a /20. Oh, so my subnet mask on my internet connection is different. And so if I go back and I look at that chart, and I look for a /20, that means I'm getting a subnet mask of 255.255.240.0, or this, and it says, well, I can have on that network up to 16 hosts, and each one can have 4,000 networks. So the campus says, we're going to take our IP address that we give you, and I don't need any more than 16 internal networks. And we get our own out of the campus because we don't want to have to do anything bad, or they think we're going to do something in here. So, but there's several others. And so our campus has decided in their build out, they don't need any more than 16. And we get one, faculty gets one, administration gets one, etc. And inside of there, if we need to, they can send out, you can have 4,094 devices. So that's that idea, that subnet mask. It can work each direction. So Class C subnet mask, if we just look at Class C, here we could break C's down. So if I'm an internet provider, and I have a Class C address from ICANN, who controls those, I can actually break it down into 64 networks. So I could resell, in this case, that to 64 customers and give them each one IP address apiece. So it really is kind of like that sliding pointer. The more we come over here, the smaller our hosts are, and the further we go this way, the bigger our network portion is. So those charts in that book are a really great way to grab those without having to do the math behind it. So there is a lot of math behind it. I'm not going to make you do it. There's tons of tutorials online, and there's tons of subnet calculators. So quite frankly, we're not going to make you do the math behind it. But one of the things that looks weird is then if I look at a chart like this, and I don't realize what's going on, do those numbers make any sense? Because here we say, here's our IP address for this network, 192.168.89.160. So let's only look at that last 160. And if I did that, and then I said internally here, we have a number of 167, 168, and 172. Does that make any sense to you? So one of the things that we have to do when you use those calculators is figure out what kind of network you're looking at and what those internal addresses would be inside of there. So we created a subnet mask like this. We broke this into a bunch of different groups. What do those addresses, what are they, and do I have enough? So the flip side of subnetting is supernetting. So I think they're really the same thing. Subnetting means you're making smaller networks. Supernetting means you're making big networks. Well, when we look at that idea of CIDR, by instead of having to say we're going to take a class C and make it smaller, or a class A and make it smaller, or we're going to take a class C and make it bigger to supernet it, what we're really talking about when I just use that slash notation, it makes life a little easier, I think. So sometimes we use it. So if I'm a corporation like Peru, and I can only get a Class C address from ICANN, and I own that address, but I need more space on the World Wide Web, I can buy a second one. Hopefully they're contiguous, and you're able to combine them using supernetting. So, but what it really is that same idea of we're taking those masks. So here's our mask that we did have. So our subnet mask, 255.255.244 or 224. So 123 in there. Here we've taken it the other direction. So it's really the same thing. What's weird is those numbers, and there's only a few sets of numbers you're going to have. And that IP address is always, for a subnet mask, is always continuous ones from over here at left over to the right where it stops. It makes a pointer in between. That's really all it does, is it creates a pointer in between those. So if I ever say here's a subnet mask and there's a hole in those ones, or it starts with anything odd, if there's not a group of these numbers, it's not a subnet mask. And I've seen that in movies where they're typing in stuff and all of a sudden they're typing in like 67 for a subnet mask. That's not a valid mask. It's got to be from left to right, a continuous set of numbers. So there's only a few different values it can actually be. And so once you do these for a while, you start recognizing those numbers and you go, oh, okay. So supernetting does kind of the same thing, only backwards. Now we've got multiple networks. So we bought 192.168.88.0, 89.0, 90.0, 91.0, and now we're combining those networks together. But the reality is, the easiest way to address those is with that slash notation. Now, IPv6 makes life a little easier in a lot of ways. Part of that is, in IPv4, we're out of addresses. And so we're coming up with every technique we can possibly come up with to try to get us more addresses. So, a couple of things about IPv6. It doesn't use that subnet mask, so it makes life easier, if anything there. And the first half of that address identify the network. So it's really literally half and half. Half is the network, half is internal. So the addresses are big enough that we can all have a piece of the pie. It's not like where we have to divide things up in IPv4 trying to come up with enough. So what we do here, so here's our prefix, and here's what they call, in this case, they call it interface ID. So this is equivalent to network and host. So we can manipulate this. This we're generally given. There are enough IPv6 addresses, though, that it's easy to manipulate. Now, some people want to try to slide that around a little bit. So a lot of times we route them or show them as, here's our address, /32. And remember, in this particular address, there's actually 128 bits. So there's a lot more to play with. And it sounds like, well, it should be twice as big, but the reality is it's much, much, much bigger. So IPv6, when we finally get it, it's going to be a lot easier because we don't have to deal with all this manipulating around because we can just get numbers and we know which part is ours, which part we can control. So here we have an example where we have a regional internet service provider. They get a little bit of a piece then for their local ISP, and it goes to a very large business. This large business, so notice they control the first 32. Now this internet provider controls the first 48. So in other words, they took that 32 and they added another 16 bits to it, to their information. Now we get down here to this large business. They have 64 bits at the end to control. And that is a huge, huge amount. If you take 2 to the 64th power, that is a huge number of internet addresses. That's one of the benefits of IPv6. But the problem is we're not ready for IPv6 here. We are the laggards. So we think the United States is the technology capital of the world, and quite frankly, when it comes to routing in IPv6 and using IPv6, we are way behind. The continent with the highest percentage of IPv6 is actually Africa, because they don't have, we didn't even give them any IPv4 addresses. They had to use it. We look at the Asian countries. Boom, here we are with China using almost all IPv6. So you've got these very large countries and continents using IPv6, and we're way behind. So my hope is when we teach this in a couple years, we're not even talking about IPv4 anymore. We're talking IPv6 on everything, and then we've moved there. But I'll tell you this, I've said that same statement for 8 years plus, and it hasn't moved. We are so locked into this infrastructure, and for us it works. We make it work, but the reality is there's better things out there, and we're stuck with this system, I think, out of lack of wanting to change. So we've all known people that don't want to change. We know football coaches, for example, they won't change a running play. Same kind of concept. We get stuck in there. So the other part of this chapter, and what I think is interesting, is that idea of virtualization, and we've already been there. So some of these you've actually seen. Virtualization on the large side, though, is a little different. We've all virtualized now in here a couple different operating systems, and that works really slick. But now imagine I'm Amazon, and I've got these giant web servers, and what I let clients do is I let them create a physical, on a physical host, I let them create a virtual server. And it's not just one. On a lot of those servers, we may have 30, 40, 50, 100 different operating systems all working at the same time. So I can move them from one machine to another. It can be independent. It gives me the ability to, for example, for data and backup recovery, it's a great thing. From the outside world, they don't look any different. But each one of those guests, as we call them, that guest can be stopped, saved, moved to another machine. And so it gives a great ability in a business. If you go into a business and they say, we're using all physical servers still, I would, quite frankly, run away a little bit. Because even if I only have a couple of servers, that advantage of putting that stuff, that virtualism, is a great tool. Because I can move it, I can stop it, I can save it. I have easy ways that I can back that data up. So one of the terms you're going to see is something called a hypervisor. So that's how that software, we manage it. So in here, we used VirtualBox as a hypervisor. Well, VirtualBox does work, but I wouldn't use it for a critical business application. It's interesting on the desktop, but if I'm going to set up servers, I'm going to use a couple of other tools. So I'm going to use Hyper-V from Microsoft or some of these other ones that are out there. So this is what it looks like. So here's your server, and if you think about it, you have multiple then guest machines. But here's a problem that I do see happening. So a company says, all right, I'm going to reduce the number of physical machines I have. I only need one physical machine, and I can put 10 different operating systems on there. What's the problem with that? If I only have one physical machine? What happens if that machine physically breaks? Yeah, you're adding a single point of failure. So you always need at least two, and usually you have far more than that, physical hosts. The other thing that comes up as a bottleneck is, notice we have multiple operating systems here running. Processor's probably fast enough. It's probably got enough memory. But notice we have that physical NIC. And so we have a lot of different ways we can do that. So in some cases, if we're going to run and we know how many we're going to run, we actually have network interface cards, and we marry them, one interface card to one virtual operating system in there. Or we team them together so that to the outside world, we still have that full bandwidth across there. So you're starting to see that. We also will put in some cases, we'll put 10, or even there are now some faster than 10 gigabit video, graphics cards, or network interface cards. So the network piece right here is kind of one of the areas we're lagging a little bit in. So we can put more servers in than we have bandwidth on those to get that out. So why would we do it? Great use of resources. In a lot of cases, we reduce the number of physical hosts, so we cut our costs down. That idea of being able to isolate things. And in virtual, I can create snapshots every 15 minutes or whatever we set up. And so somebody like, say, Jacob here, puts a virus on a machine, on that server, I just simply stop it and I roll back 15 minutes and I'm back. So backups are great. Recovery's back. So a couple of things that happen. We can have that single point of failure, though. Does make life a little more complex. If we put too many virtual guests or servers on a host, we can have some performance issues. And the next part is that licensing cost, because it can be very expensive. Every time I put up a copy of Windows Server, for example, it could cost me anywhere from $600 to $2,000 depending on what the licensing model for that is. Now, Microsoft has actually come out with, on their latest version, says, all right, I know you guys are going to use virtualization, so we actually, if you virtualize with our tool called Hyper-V, you buy one copy, we'll actually let you run two, license free. So there are some pieces and some companies that are on board with that. So VMware is probably the biggest player in the game, and they have a ton of really slick tools. So one of them they have is something called vMotion. So even when they're running, I can slide it from one machine to the other, that operating system, and that I haven't seen, for example, in Microsoft's Hyper-V. It may be there now. Here's the advantage to some of these. Hyper-V actually runs for free. We get something for free included with Windows Server. Yay. Now, when I say that, though, if I'm going to run Linux operating systems, I'm probably buying VMware to set up there in the back end. So there's some others, XenApp and some others that are out there. But really, VMware and Hyper-V are probably the two biggest players in that game. So it's a great tool. Almost every server now is being run in virtuals. So if we can virtualize parts of that, Now we can make more parts of our network virtual. So we're getting more and more pieces. One of the things we do in a lot of cases, and I've looked at it, but I can't afford the licensing costs since we have no budget for the lab, is the idea of virtual desktops. And so a lot of companies are going to that. When you log into a computer, you're getting your own virtual desktop, and it's sitting on a server. It's not sitting on that local computer. Well, the advantages then include things like I can have security better. I can keep all my documents on the server so they don't go off on a computer individually. And even things like software licensing, because software is expensive to license. So we just signed a license for something called SPSS. Has anybody heard of SPSS in here? No? You guys haven't done a stats course where we talked about SPSS. So it's probably the preeminent statistical modeling package out there. Works really slick. Problem is it's really expensive. And the first effort when we wanted to license it for a couple computers on campus was it was going to be about $8,000 a year per machine. Have you seen our budget at Peru? That's not going to work. But people doing research, it's the tool that most of the time is what they're looking for to see. And so the last effort they came up with was much more reasonable. It was about $8,000 for several licenses. And the way we monitor those is they're on kind of that virtual network, and they're checked out. And so we can do that with software now in that virtual environment. We check it out. So 3 users, I think it is, can use it at the same time or concurrently. And then we can check it back in. So even on a small business, how many people are all using Microsoft Office at the same time? Maybe you could cut your licensing costs down. And it's expensive. Microsoft Office on a corporate volume license, the last one I priced was $428 an installation. That's a lot of money for a small business. If you have 50 machines at $400 a license, that's pretty expensive. If I could cut that down in half, because we know that everybody's not using it at the same time, these virtual pieces get to be a really great way we can conserve resources. So, when we look at this idea, that network connection is one of them that we need to think about. And you can actually have virtual switches. On our virtual box, we didn't care how it got there. And it actually creates a virtual switch, and it assigns an IP address. But we can actually do what's called bridge into the network. So we can create it so it gets a network address on our main network, not in that virtual one. Because remember when I showed it up there and we had I did the IP config all, we had a different address for VirtualBox than we did for our main network. And so they wouldn't be able to talk to each other normally. So we can actually bridge them across. So make sure you've read about virtual switches. So in other words, that's what we're looking at, is this idea. We have a physical network interface card, and then we have virtual network interface cards internally. And so when you set up VirtualBox and you ran Microsoft Windows and you ran Linux at the same time, that's what's happening. You have one physical connection, and it's splitting off and going in multiple directions. And again, that's kind of where the bottleneck right now seems to be in some of this virtual technology. We've got the processors fast enough, but we can actually do it this way, where we have a router or a switch, depending on how we have it all set up, this physical connection, and then they bridge in. So those virtual switches can be configured in a lot of different ways. It depends on what our usage model is. So the most common one that I've seen is what we call bridged. And bridge mode says it connects out, gets its own IP address, all that information from that DHCP server on the main network. So it goes out, gets its network, and from external to that server, I don't even know that it's not a physical machine. And so quite frankly, that's the one we use most often. So that's this idea of a virtual connection. So here's my physical network. It's getting all this information in that address from the physical network. And we can actually also, we still call it bridged, but we can put them in statically if we know what those are. there's some advantages to doing it on the router. That way, no matter where that instance fires up. So if it's on any one of 30 different machines, it's going to go grab an address itself. So make sure you've looked at these different modes. Bridge mode seems to be the most common thing we use, or at least in my experience. So we've got some really nice pictures in there. Make sure you've read through there. There are now all kinds of virtual servers and appliances and all different kinds of things. So we created our own instance on VirtualBox. If you look at something like virtualboxes.org, you can find there's already pre-configured installation packages. Somebody's already installed it, got all the tweaks done, and you can do it from everything from email to remote access. They're all available out there. So that virtual world is kind of interesting. It's already pre-configured. We slide it into our hypervisor of our choice, and boom, we're set up and running already. So what that leads is this weird idea of something called a software-defined network. So we take that virtualization and now we're extending it over the entire network. Oh, kind of weird. And so when we do that, maybe it makes a little more sense of these idea of these planes. So here we have virtual services, and here we have our data planes. So we're creating this entire virtual architecture where everything cooperates together in this big virtual or very easily manipulated environment. Well, when we do this, think about on our desktops here. Everybody's got their own hard drive on a computer. And it's got, in this case, 128 gigabytes. We're not using all of that. If we're truly virtual, all of that storage space could be in one big pool. And so if somebody creates a big video file, it doesn't necessarily set on one physical device. It could set anywhere on that network. And so we're starting to get to that point where we're being able to share all those resources. So there's a lot of interesting work done in virtual right now. If you walk into a company and they're not talking virtualization, then you probably need to get them on board with the idea of virtualization. Now, what's weird, and I'm not sure I like the way the book organizes this piece and throws this in at this point also, but the other way we break up our networks is with something called VLANs. And VLANs are virtual LANs, but it's not quite as intensive as what we're talking about when we're talking about this entire virtual environment. So VLANs really means by each port on a switch, we're creating what's called a VLAN tag. And so that tag is really just a number that says, all right, this particular port is in VLAN 1. This one's in VLAN 2. This one's in VLAN 3. And they're separated then. So even though they're all plugged into the same switch, so even though these are all plugged in to the same group of switches, I can't see traffic from VLAN 1 to VLAN 2 or from VLAN 3 to VLAN 4. And that's the only way I can get traffic from one to the other is by going through that router, and I can control those rules about how we do it. So here on our campus, we have several VLANs. So one VLAN is for wireless guest access on your Go Blue network. One VLAN then is for faculty on the network. And so we can have these separate VLANs set up so we can create different pieces. So a lot of times we would set up one for voice over internet, and voice over internet may be on VLAN 3. And what we do when we set up our switches then, we can set up each switch port to add that tag to a particular device. So it's really set up for security, creates a way to block that traffic into smaller pieces. So we break a large network into smaller pieces using VLANs. And that really happens on that switch side. So we put a port, so every port in a switch can be set up at a specific VLAN. So this switch, even though it has both 1 and 2, it trunks that information then to another switch. And so VLAN 1 can communicate with VLAN 1 on this particular switch without any problem. So all it's really doing in those IP packets is adding an additional item in there. So those VLAN tags are really great. Here's one problem with them. So the switch, we hard code in the switches most of the time is the way we do it. And so we say port 1 is VLAN tag 10 or whatever we happen to be tagging each one of them. Somebody comes along and unplugs a bunch of network cables and we don't have a diagram showing which VLAN is in which one. It's going to take you a long time to reset that up. Or you have a switch die and you didn't have that backup, that configuration backed up somewhere, so you can put another switch in there. Yikes. It can get horrifically bad pretty quickly that way. So VLANs are a way we break them up. VLANs in theory, unless you get with some very odd proprietary things, are universal from one switch to another. So in other words, I can create VLANs and they'll go over Netgear switches and they'll go over Cisco switches and HP switches. So the switches tend to need to be a little more expensive. Your switch you buy at your house isn't going to have VLAN capability on it. It will pass the VLAN tags, but it won't be able to set them up. So the other last piece in here I want to talk really briefly about is something called spanning tree. And so spanning tree, one of the problems we have, we like the idea of redundancy. So we want to put everything in big giant loops, we would think. So everything has multiple connections. And so if I look at this particular configuration here, so spanning tree says, all right, I know that this particular switch connects to B and to A, and then there's a big loop. So B also connects to A. What happens, though, because we created this path, we can have traffic that would go continually because it doesn't have a landing destination. So spanning tree is a way that we temporarily block off things to only have a single path. And so here we've blocked off this path, we've blocked off these two paths, and so everything has a single path. If this path goes down, then spanning tree will open up this other path that's normally blocked. So spanning tree is a way we can connect multiple computers or multiple devices with multiple connections and not have that endless loop of packets that doesn't know where to go. So spanning tree is really hard to turn on. On most switches, it's as simple as we say we're going to turn it on. The better the switch, the better the spanning tree protocols. It does rely, in some cases, on some manual setup. Most of the time, though, if I buy all my switches from Cisco, for example, and I turn on spanning tree, I'm pretty decent in what it's going to do because it's going to select what they call a root bridge, or the one that controls the first path. And it's kind of interesting in how that works, but a little outside of stuff we want to go into before a heavy Thanksgiving dinner. But it actually takes that MAC address in most cases and uses that as a who's got the lowest address. So kind of like when you pull out your dollars and you play who's got the highest card value of $1, that kind of thing. So we want to look at a couple of switch configurations. So unmanaged switches. They don't have an IP address assigned to it. They just plug and play. And so underneath every group of desks in here is an unmanaged switch. So it's just got a bunch of ports. It's got one connection in and multiple connections out. A managed switch, though, we can set things up in. So those unmanaged switches we use in here because of the great planning of when we redid the building, there's 8 computers in each one of these pods, or in this case 10, just because of the layout of the room. there's 6 internet connection jacks in there. The numbers don't match. And to make it an easy way to do it, we just put an unmanaged $25 switch in there. Managed switches, though, we can log into, we get to make choices, we get to implement VLANs, and we do all kinds of pieces like that. Managed switches tend to be more expensive. We also need to worry about a couple of things. So, they almost always have an interface, a web interface. That web interface then tells us we need to change that default username and password, because almost every switch will allow us to do things that we could do bad things on the network. From sending all of the data on that switch into a single port and monitor it. So what things do we pay for? We pay for better interfaces. We pay for better speed. So right now, a pretty decent managed switch, depending on how much hand-holding you need. So a 48-port switch like we use for this room can range anywhere from $500 to $600 all the way to $10,000 to $20,000, depending on what features you want. How fast? Well, right now I wouldn't get anything less than a gigabit per second switch. There are 10 gig per second switches out there now. Probably a little much for here in our cabling, but a gig per second switch. We know it needs to manage VLANs. So what kind of things we do with that? A couple of other pieces. Wireless does something very similar. So wireless can have VLANs. Wireless VLANs are kind of interesting. So everything else is physical. So it plugs in. Each port has one physical port. Wireless, though, it's the same controller out there, the same access point that gives you Go Blue and gives faculty and several different other ones. So in a wireless VLAN, it's got to map a VLAN to an SSID, that name you create. And so it does that on its software. If we have multiple access points, then what we're really doing is we're looking for ones that would be controlled with a controller of some sort. And so for those of you in here, I brought out the D-Link one we used to use in the lab. It would run 256 devices. Now there are controllers out there. So for example, Ruckus has ones that will run 10,000 or more wireless access points distributed out all over the entire world. So they're using them, for example, in Shell gas stations, and they're managing from a central location every Shell gas station wireless. So how much you're going to spend on those things gets to be interesting. So what all of this really is doing is trying to give a better management tool. So you're breaking your traffic up, or you're expanding your network to fit your size needs. How do I do that? And so these are a couple of those tools. That virtualization gives us a lot of tools we can use, even to the point we use it for almost everything here on our college campus. So if we want to test out something new in Blackboard, we don't put it on the live production server. We have a virtual system that we can deploy patches for. And then we can say, oh, no, that didn't work. Let's go backwards and come back there. So all of these pieces tie together in that idea of management. So again, for this week, back out of here real quick. And I did close it. My bad. So the only thing you actually have due this week is a quiz. And then we have 2 weeks left and we're out of here for the Christmas break. So, one real quick thing. Is anybody in here not registered for classes in the spring? Vinsky, you're looking kind of guilty over there. Our website? It could be. They've had a lot of traffic. I hope not. But if you haven't registered, I was looking through some courses today. There are a lot of classes down to 1 or 2 seats available in them. So if you need that class in the spring, especially for those of you that hope to graduate, and it's a required course, You feel that guilty look there, Christian? Like, what? So make sure you've gotten registered, talked to your advisor, figured out what you're going to take so you can graduate.